Okay, so here's our first lesson in chemistry. And we're going to talk today about, first of all, really just what is chemistry. And so I'd like to actually start with the first line I have written up there. It says, chemistry is the study of change. That's the definition of chemistry. My question is, changing what? What sort of things change in chemistry? And really, the thing we want to change is matter. We want to change matter. When we undergo chemical reactions and cool things happening, we're trying to change the stuff around us. Like, here's some examples. Metal rusts in the rain. That would be a good example of chemistry. Because metal used to be this shiny, hard, something firm that we can make a car out of. And over time, as it sits in the rain, it eventually rusts and corrodes, it becomes weak. Or hydrocarbons combusting. This would be like when you use your barbecue to burn propane. There, we're changing things. Or even if you want to make wine, that's grape juice fermenting. The whole key, though, is this word here, change. So, quick question, though. Do you guys actually know what matter is? Like, when I use the word matter, what is matter? Everything's not a... Because not everything's matter. That's close. That'll get better. Write this down, okay? When we do notes here, I'll tell you to put little things in the margins here. Matter has two requirements. It has to take up space. It definitely has to take up space. But let me give you an example of something that's not matter that takes up space. Fire. Fire clearly takes up space. I have a fire in front of me. I can see that the flames get this high. But fire is not matter. Fire is actually energy. So there's actually one more requirement. It has to take up space, and it has to have mass. Those are actually the two requirements. I don't think so. We might, but...
I can look through there. I just thought maybe you had some.
For anybody who doesn't have notes, then just print them off after class, right? Because these are on the website. Although, Val, if you really want, maybe grab that computer right there and see that you can find them on my website. Okay. Matter is anything that takes up space and has mass. Okay? It has to weigh something. Fire doesn't actually weigh anything. Energy does not have weight. Okay? But it also has to take up some space as well. It literally has to be like stuff. Sometimes we talk about matter as being stuff. Like, this is matter because it takes up space and it actually has some weight to it. Okay? Whereas like certain forms of energy, for example, like light. Light takes up space. Look, there's light all throughout this room. It is clearly taking up space. But does light weigh something? Yeah, so light is not considered matter. Long story short, I liked Valerie. I liked your definition. Matter is almost everything, but it's not everything because there are a few things that don't really count as matter. Our goal then is to try to talk in this class here about how molecules change from one to another. How does these initial things change to these products here? Here are some things that hopefully we're going to see over the course of our month together. When we're looking for chemical change, here's some good examples. Like if there's a new phase of matter being produced. For example, if something blows up and it goes from being a solid into a gas, probably a chemical reaction took place. Precipitates formed, new smells and odors. I should actually stop. Do you guys know the word precipitate? What does precipitate mean? Yeah, in everyday life, precipitate sometimes means rain, but in chemistry, this picture right here is a precipitate. If you have a solution and there's like a cloudy kind of suspension inside of it, we call that a precipitate. So if you ever see something like that, it usually means there's a chemical reaction. What we're going to do in a lab, and we're actually doing our first lab on Thursday, is I'm going to have you guys make some observations on some different chemicals and chemical reactions. Okay? And I can really break it down into two categories. There are observations that we consider to be qualitative and quantitative. Okay? Let me start with quantitative. Quantitative observations involve numbers. If you have a quantity, I can assign a numerical value to it. So you may even want to write down that these ones here involve numbers. Let me give you an example of a quantitative observation. This would be like saying that it weighs 10.2 grams. So there's a number attached to it. That's how heavy it is. Or I could say that it was 7 degrees Celsius. That's an observation. Those would be observations, though, that have numbers associated with them. Whereas a qualitative observation is really based on a quality, and usually these are just things that don't have a number associated with it. Like, for example, it could be yellow. Right? There's no number associated with yellow. Right? You could say that it is solid. You see the difference here? And so when you're observing things in chemistry, you're either looking for things that are like adjective descriptive words, or you're looking for things that are numerical values. And both have value. Right? We don't just want to have numbers, but we don't want to skip out on recording things that are like numerical. So when we're talking about these properties, another way we can break them up is into things called chemical properties or physical properties. Okay. In general, if it's a physical property, it's about its appearance. As I'm looking at it, sometimes I like to highlight things. As I'm just looking at it, I could describe things, like say its boiling point. Right? Would a boiling point be a quality or a quantity? A quantity. What's the boiling point of water? 100 degrees Celsius, right? 100 degrees Celsius would be a quantity. Let's say I was talking about water. Okay, water has a boiling point of 100 degrees Celsius. What color is it? Okay, clear. Well, if I said that it was clear, then that's not a quantity, that is a quality, yeah. So you can have quantities and qualities, but you can also have them based on physical appearance properties or based on how they react. You guys can see how there's a few different ones here. Here we've got things like boiling point, color, and magnetism. These are properties that we talk about just about the compound by itself. Whereas these are how it reacts with something else. Like, for example, how does it burn? Because some compounds, they burn. Other ones, they don't. But that's more about how it reacts with somebody else. Or like, what happens when you put it in water? Some things, when you put them in water, they dissolve. Some things explode. Some things just get wet. What's up? Absolutely. Of course. Do you guys get the difference here? A physical property, then, is really something that's just about the compound by itself. It's its appearance, it's its natural state. A chemical property, then, is, well, what happens when it reacts? That's really the key word here. How does it react with something else? Okay. Now, today I'm going to do kind of more of the lesson teaching part here, but on Thursday I want to actually do a lab where we try to show you some of these properties. So you actually can hands-on try to see this. Similar to that, we can talk about our changes in the same sort of way. Have you guys ever heard the term physical and chemical change before? Sometimes people have learned this. A physical change is literally where you're just changing the physical properties. Usually it's the state of matter. I found a diagram online that I thought really helps. Like a physical change would be you take a solid and you melt it, or you take a liquid and you evaporate it. Right? But at the end of the day, let's say this was water, which is H2O. It's still water in all three of these kind of diagrams here. Here's water as a solid, here's water as a liquid, here's water as a gas. But in all three cases, it is still water. Does that make sense? We haven't actually chemically changed it into something new. All we're doing is we're changing the state of matter. Sometimes we call this the phase. You guys ever heard that word before? The phase of matter? Here's the real key to a physical change. A physical change can be reversed. Let's say that I have an ice cube and it melts. No, my ice is melted. Is it the end of the world? Or can I fix that problem? Just freeze it back up again. Yeah. Physical changes are reversible. All I've got to do is just undo the change. Now, sometimes it's not a lot of fun, but it's still possible. For example, here's a sheet of paper. I have now given it a physical change. Is it still paper? Yeah. I didn't actually change what it was. Now, can I undo this change? Well, yeah. I can tape it back together. Okay. This would be considered a physical change. But I'm not going to do this because I don't have the safety set up right now. What if I lit this on fire?
You should do it.
I don't have the safety stuff set up. If I light it on fire, though, is it still paper? Now it's our charred ash and stuff like that, right? And furthermore, can I unburn the sheet of paper and go back to what I started with? No. We'll do this on Thursday. So let me give you some examples then of some of the physical properties and some physical changes you might see. This is a pretty good list here. And I might recommend star this list, okay? Because this is going to be something I'm going to ask you on labs and on tests and on quizzes. Not a very good star, but thank you for the vote of confidence. There. There's a star. It got better. It got better. Okay, so here's some examples, and I'd like to talk through these one at a time. Like I said, my teaching style is quite different than, say, Lav's. Okay? What I want you guys to do is engage in this conversation here so that as I talk through these things right here, you know what I'm talking about. So maybe write down what I say. You don't need to write down what's there because it's ready for you, right? So, first one's easy. You guys know what color is. But what about the second one? Does anybody know what a luster is? Courtney? Yeah, shininess, basically. Certain things are more shiny than others. For example, one of the things that has the most amount of luster would be a diamond. You know how like a diamond will gleam and glitter in the light? That has luster to it, right? Its ability to reflect things. Whereas, I mean, even if you look at my board right here, this is a good example here. This right here has a little bit more shininess to it because the light can gleam off of it. Whereas this section right here, it's more of a dull kind of surface to it. You guys get the difference between the two? Luster is like shininess, the ability for light to reflect and gleam. Most people know these next two off the top of their heads. Melting point and boiling point. Melting is where something goes from a solid into a liquid. And boiling point is where it goes from a liquid into a gas. Yeah. Now, it's possible. It usually combusts first, but it is possible to melt it. Now, these two things right here, they're definitely going to be quantitative, right? Because they're going to have numbers associated with them. That makes sense? But hardness would then refer to things like, often they're used for jewels and rocks and stones, as to how thick it happens to be. This right here is solid. This right here is also solid. And the wall over there is also solid. I feel pretty comfortable doing this. I don't want to break it, but I could do this. But I'm certainly not winding up at the brick and trying to punch it. Right? Because hopefully you'd agree that clearly everything has a different amount of, well, the hardness is the word we use, right? Hardness is also referred to as the ability to scratch another surface. For example, if I were to take a diamond is one of the hardest things we know because a diamond can scratch just about everything else. Right? Whereas if I were to take this paper right here, do you think I could take this paper and scratch the concrete? But do you think I could take a piece of concrete and scratch the paper? You see the difference there? That is harder than this because of that can scratch this. Does that make sense? So really, that's the key indicator for hardness, how it can scratch something else. Okay, the next two words are ones that I don't think grade 9 students are familiar with. They are malleability and ductility. Okay. Malleability refers to the ability to turn it into a sheet, usually of metal. Okay. You know how you can have like a like the frame, aluminum frame of your car, perhaps, or iron? If you can make it into a sheet of metal, that's known as its malleability. And there's a lot of things that you can make into a sheet. But here's an example of something you can't. I cannot take oxygen and make a sheet of oxygen. But I can have a sheet of copper or a sheet of nickel. Does that make sense? If you can make a sheet of metal out of it, it's malleable. Ductile is similar but different. Ductile is about making it into a wire. If I can bend it around as a wire, it's ductile. Again, most metals are ductile. Like I can make wires out of copper or out of zinc or out of nickel. But there's some things I can't make a wire out of. Like there's no such thing as a wire made out of potassium. It's just not possible. So malleable has to do with can you make a sheet out of it? And ductile is can you make a wire out of it? Most of the time we're talking about metal things. Crystal shape hopefully kind of makes sense on its own. Like what kind of shape does it have? Do you guys know the word solubility? What does it mean? That's the key word. Yeah, this is about whether it dissolves. Yeah. If you can take it and put it in water and it dissolves and kind of like disappears, that's soluble. I'm going to skip density for last. You guys probably know what conductivity means. It means that it conducts electricity. I'm going to show you a test on this on Thursday. And the last one here, density. Density is kind of a measure of like how thick something is. Density is measured in how much mass there is per volume. Those are actually the two requirements of matter. Matter has to take up space, which is volume. It has to weigh something. If you want to find something's density, you take grams and you divide by milliliters. And that'll tell you how dense something is. The most dense substance known to man is lead. Lead is very dense. So dense, actually, that it's able to block X-rays. You guys notice anyone go to the dentist and they put the lead vest on top of you when they take the X-rays? Lead is actually so thick that X-rays can't penetrate through it. Yeah. Gold is also pretty dense. Let me give you an example of something that is not dense. Nitrogen gas. Nitrogen gas makes up most of our atmosphere. There is a lot of nitrogen gas all around here. I can put my hand through nitrogen gas and bat it everywhere. I can even do that to water. Water is not very dense. I can actually swim. I can swim through water. I cannot move through lead. It is too dense for that. Does that make sense? Here's a slide. I'm not going to read through it, but here's a slide that kind of re-talks about a lot of the properties we just mentioned. I need you guys to know what they are. So, any questions so far? Okay, let's move on. Okay, well, if those were all physical changes, then the opposite side of a physical change is a chemical change where it reacts with something else. We're taking copper and putting it with water. We're taking copper and putting it with iodide. We're taking copper and putting it with sodium. And we want to see how it reacts. And whenever you have a chemical change, here are some of the common things. I found this picture on the internet. These are some of the common things you'd see when you have a chemical change. And we've already kind of gone through a list. Often there's heat or light or smell or sound or color change. Those are good examples of a chemical change because you've now made something new. The change is irreversible because you've made something new. Let me go back to my example of paper. When I rip the paper in half, it's still paper. But when I burn the paper, it's now not paper anymore. Now it's charred ash and smoke and dust, right? Because what's happened is it used to be white. It used to be a solid, right? It used to be somewhat bendable. As soon as I burn it, the leftover stuff doesn't look like this at all. You know what I mean? And more than that, I can't reverse it at all. Okay? So one of the things I need you guys to be able to do is tell me the difference between a chemical and a physical change. Okay? So I've got a little activity here on this next slide. We're just going to walk through this as a group. I need you guys to tell me whether we have chemically changed it or just physically changed it. So you guys can yell these out here. If you break a window, chemical, physical. Physical, yeah. It's still a window. It's just in pieces. Let's say you bake a cake. Chemical, because you started with sugar and flour and eggs, and now it's yummy, delicious cake, right? Like eggs raw and flour raw do not taste good, right? But chemically change them, and now it's delicious. Slicing bread. Good. Crushing a can. Frying an egg. Yeah, it's different, right? It used to be runny, now it's solid. Ice melts. You can undo that, right? You just freeze it again. What if you use a battery? Depends on the kind of battery here. Because technically there are rechargeable batteries. Yes, I get that. But ignoring that fact right there, because in order to charge you have to do another chemical reaction, really this is a chemical change because the battery is now dead. So that's a chemical change. Yeah. I know you can sometimes recharge specific ones, but that's not what we're really talking here. Fireworks. Yeah, I mean, they give off light and sound and heat and... Fire is basically the same thing as fireworks, right? What about a car crash? Probably physical. With one exception, though. Maybe if... like if something were to explode or something were to rust as a result of that, maybe. But yeah, I mean, if we're just talking a fender bender, you still have a car. It's just now bent. Making popcorn? Chemical, right? You used to have kernels. They're now fluffy, delicious, buttery things, right? Chopping wood. I get the impression that most of you guys seem to get the two of these figured out, right? So, physical, you can undo it. It's more or less just talking just about the one item. Chemical is where you react with something else, and something new gets made, and you can't undo it most of the time. Cool. Okay, well, one other thing we want to talk about today, then, is when we're talking about this matter that's going to undergo changes, either a chemical or physical change, we want to be able to categorize that as well. So today is actually a lot of words. It's a lot of naming things. Today we're going to talk about the names we give to matter. Here are some words that maybe you guys have heard of before. Atoms, molecules, elements, compounds. You guys ever heard those words before? Cool. Okay, well, let me go through my next slides and we'll talk through them one at a time. So, the first thing I need you guys to know is what's called a pure substance. Okay? A pure substance is where you literally just have just one thing. Just nitrogen, just water, just, pick this. Literally just one thing. Now, pure substances could be elements, or they could be compounds. One day I'm going to give you guys a periodic table, but you guys can see the big one at the back there behind Paris and Sydney. So want to call your sister's name. I'm so sorry if I do. You guys see the table back there, though? Okay. If it's on that periodic table, it's an element. Like, say, hydrogen, nitrogen, oxygen. Those are elements. Okay. Those would be considered pure substances. But we can also combine them together into compounds. Like, for example, CO2. You guys know what CO2 is? Yeah, carbon dioxide. This is a carbon and an oxygen. But this is still, even though there's two parts to it, we can still consider this a pure thing because there's just one item. Or water, for example. This is water. This one is carbon dioxide. Individually, they're both pure. And I've got a picture over here to kind of show you this. This is an element. There's just one thing in there. This thing right here, even though they come in groups of two, there's still only one type of thing there. Even this picture right here is still pure because each of these molecules we have, see how they're all the exact same? This thing right here is the non-pure substance. You see how you have one of these and one of these and one of these? This is no longer pure. We give this a new name. We call it a mixture. You see the difference? A pure substance is literally just one thing. Whether it's an element or a compound, you've only got one item in it. But a mixture is where you have combinations. Like, for example, this little batch of candy right here. Right? You've got some jujubes and some red ones and some purple ones. If you were to have only one kind, it'd be pure. Like, for example, if you could buy just red Smarties, I guess that would be pure. But when you buy Smarties, you get some red, some blue, some brown, some black, right? Well, then that's a mixture. There's no black Smarties? Ouch.
Smarties aren't even a thing anymore. It's all about M&Ms now.
I don't suppose I could go back to my lesson, could I? You got so distracted on Smarties. Okay. There are two types of mixtures. I want you guys to know these words. And you can pronounce these a little bit differently. You either call this one a homogeneous mixture or a homogeneous mixture. Depends on how you say it. Everyone says it a bit different. And then the other one is heterogeneous or heterogeneous mixture. Okay? However you want to say it. Okay? Most people probably say homogeneous and heterogeneous. The difference between these two types of mixtures is basically this. can you see a difference? If you can see the difference in stuff, it's a hetero. But if it looks the same, then the prefix is homo or homo. Like, for example, pudding. Pudding looks the same all the way throughout, right? I know that there's milk and sugar and chocolate sauce. I know there's definitely more than one thing in pudding. It's not pure. There's definitely more than one thing there, right? But if it all mixes together really nicely, you might call it a solution. Whereas right here, my Chex Mix, I can clearly see, hey, look, there's a red one. Hey, look, there's a green one. Hey, look, there's a black one. Or is that brown? Yep. Here's another example of a heterogeneous mixture. When my girls get sick and we have to have Tylenol. Tylenol is actually a good example of a mixture because there's more than one thing inside of it. You guys ever notice that certain things, they actually separate into layers, where there's like the top layer and the bottom layer? You actually have to shake up your Tylenol before you use it so that it's like a nice uniform mixed solution. Okay. Then you don't get better. What about milk? Guys, stay with me, okay? I'm almost done. Stay with me. What about milk? Why should milk be fitting in the heterogeneous mixture? What are the components of milk? What is inside milk that's not necessarily, that can be separated? Okay, when you go to the store, your dad asks you to go to the store and buy milk. Is there just one type of milk at the store? Okay, let's pause on that thought for a second. There's skim milk, there's 1%, there's 2%, there's 3.25%. Okay, so pause for a second here. Let's just stick to the percentage milks. What is the percent talking about? Fat and cream there is, yeah. So even though milk looks like it's a solution, it really depends on the type of milk you have. Because if you're drinking the homogenized milk, the red color one, that's what we get at least, red or pink, right? There's more, guys, shh, please, be quiet. There's more cream and fat content in it. And if you let it sit for a little while, the fat will kind of rise to the top, depending on how creamy the milk happens to be. So even though it looks like it's a solution, it's the same throughout, that's actually not true in most types of milk. I've actually got a slide here then kind of talking about the different types of mixtures. There are things known as matter, which either can be pure or a mixture, and then there's elements, compounds, or the two different types of mixtures. So another task I might need you guys to be able to do is, if I give you an example of matter, can you categorize it for me? Let's try an example here. Oxygen. Where in this chart would oxygen fit? It's an element, yeah. Oxygen is a pure substance because it's an element. What if I were to talk about Kool-Aid? Where would you put Kool-Aid? Okay, is Kool-Aid pure by itself? No, because clearly there's crystals mixed with water. So it's definitely got to be a mixture, but what type? Is it a homogenized or a heterogeneous? It probably would fit here because the Kool-Aid just all mixes together, right? What if you were to buy Chex Mix? So that's like where you have like pretzels mixed with like Cheerios, mixed with Shreddies, mixed with peanuts. You know what I'm talking about? That kind of mix? What would that be? Yeah, it would be we'd actually call it a mechanical mixture. Here, let's call it trail mix. If we had trail mix, that would go there. What about water? Water's a compound because water is H2O. It's got hydrogens and oxygens. So water goes there. What if I were to give you orange juice? Where would orange juice fit? Probably a suspension, actually. Yeah, orange juice would probably go here. Because you know how orange juice has like little bits of maybe pulp and stuff inside of it, depending on whether you filter it, right? But unless it's pure like Sunny D, if there's any sort of pulp type stuff, it's probably a suspension because there's stuff suspended in it. Okay. Let me move on here. Oh, that's my last slide. Perfect. Good timing. How long was I talking for? Half an hour almost to the second here. So, here's what I need you guys to do. I'm going to leave this running here, though. In terms of my learning cycle, I'm going to break our unit up into 7 different lessons. Okay, we've now done one of them. Okay, I hope that as we did this was a little bit more efficient than you guys writing the whole time, because I want you guys to write down what we talk about, what we say. Okay, so please give me your attention still. Don't pack up yet. Okay, we're not done. Okay. But it goes beyond this. What you guys really should do now is re-look over your highlighted notes. Maybe re-watch this video on my website later, because I mean it only took half an hour. You can re-watch it. Some kids watch it on like 1.5 times speed, so they can see this again. Okay? But now that I've given you guys that first step of knowledge, the next thing I need you guys to do is now apply it. You should now try this. Okay? So I really want to encourage you guys to be digital students. Okay? I'm not going to print anything for you. Okay? I really want to encourage, if you guys want to print something, the computer is normally over there. Miss Costalanski has it right now. But if you want to get something for my class, I list everything down here. So there's 2 things you guys can start to work on. Augusta, please, focus, please. Know your name, so I'm going to call you guys out. Here's the first thing you guys can work on. If you have your phone, you don't even need to have a sheet of paper to do this. You can click on chemistry assignment number 1. This is one of the things we're going to do. And you guys can probably start answering some of the first questions. Like, for example, question 1. Can you guys now define element, compound, and mixture? We just talked about it in class. Could you give me an example? Question 1. Or number 2, what physical property am I describing in each statement? For example, if I tell you that oxygen melts at 218 degrees Celsius, that's a melting point. If I tell you that silver is shiny, you've got it. A little too fast. Or this one right here, I might ask you, tell me whether these are elements, compounds, and mixtures. So this is one of the things you guys can work on. I find a lot of times students, I finish my lecture part and they're like, class is done. And I go, no, wait, class is not done. I know there's maybe only 10 minutes left, but what I really want to encourage in you guys is don't just call it a day. Spend 5 minutes working on like 1 or 2 questions a day. Okay? If you do this a little at a time, it works much better than trying to do the whole assignment all at once. Because you guys should be able to answer, say, the first, second, and third questions. And honestly, if you work hard, I bet you'll finish questions 1, 2, and 3 in 10 minutes. More than that, you guys have flex time right after this. You could use your flex time to work on this as well. Okay? So that's one task you can work on, is your assignment. The other task you can work on, and this one you will have to print, is the lab safety project. We're going to do a lab on Thursday. And before my kids get to work in the lab, I want them to actually know how to be safe and how to find things. So lab safety project is right here. You can probably start working on this. Tomorrow, I'm going to show you guys WHMIS symbols. So if you already know these WHMIS symbols because you've learned them in the past, this is one of the things I'm going to ask you to do is label the WHMIS symbols. Another thing we're going to do on this task is there's a cartoon I found here of all sorts of things that kids are doing in the lab in this cartoon that are totally wrong. Yeah, there's a snake on the table here. Broken beaker, listening to music, drinking poison. Yeah, that's a smart one. So, on this one right here, all I want you to do, give me your attention, guys. So I want to stop in a second here. I want you to find 10 different examples of inappropriate lab behavior and tell me why they shouldn't do it. Third thing, this is actually directly out of our textbook. All I've done is I've taken the chart and I have cut out a few words. Literally, I just want you to fill in the blanks of some lab rules. Okay. This is the last one that some kids may want to start working on, though. To me, this is the most important one. This is a picture of our classrooms, mine and labs in the middle room here. This is my room right here. I'm sitting, give or take, right about here. This is the first dividing wall, the second dividing wall. What I need for you guys to do is I need you to know where stuff is, especially if we need to find, say, a fire extinguisher, a fire alarm, the gas safety shutoff. What was that? No, they're not, actually. Unfortunately, they put almost all of the fire alarms way down a hallway. So what I want you guys to do is I want you to make a little map where you find where the eye wash stations are, where the emergency shower is, where the fume hood is. I'm actually going to show you guys this tomorrow when we talk about lab safety. But if you could, can you print this off and get started on it now? So those are 2 tasks. Now, I know you only have about 5 minutes, but honestly, you can probably get started on one of them and just get a little bit going. Okay, so tomorrow we're going to do a lesson on lab safety, and then on Thursday we're going to do a lab, and that would be the third thing you could do. is you could then print off the lab chemical and physical properties. Okay. I'm not going to print stuff for you guys. Okay. I really want to encourage that you guys are able to be independent. Okay. So if you need, there's a computer, there's printers. Okay. If you can, just use your phone. Okay. But even if we have 5 minutes at the end of class, don't waste it. Okay. Use it to do something, because I bet you can finish at least question 1. And that's better than nothing. Sound good? Okay. Find something to do.